Hello, my name is Lindsey Boyle. I am an undergraduate in physics, and my research is over the stability of triple stellar systems with exoplanets. Now, in the universe, there are a multitude of different types of solar systems, from a single star system all the way up to a 7-star system, and a percentage of those systems contain exoplanets. There are currently 30 known triple stellar systems with exoplanets, and the main goal of this research is to determine if the triple stellar components of those systems are stable based on Hill's radius. The work being conducted in this paper is based on a catalog that is currently in the final stages of being written to be published with Dr. Kuntz, and all values are being taken from that pending paper. A triple stellar system is a binary and a single stellar component that orbit a common point, close enough to be considered one system, as shown above in Figure 1. A planet will be found in one of 4 orbits, either orbiting one of the stellar components in an S-type orbit, or orbiting the binary in a P-type orbit. Python was used to create a program to calculate the values by utilizing the equations shown below taken from Walker 1983. For the system to be considered stable, the limiting value of ratio alpha, or A1 divided by A2, now known as alpha critical, is stable such that alpha is less than or equal to alpha critical, which is the same as where the total angular momentum squared times the total energy of the 3-body system for the actual and critical values are the same. So the actual is less than or equal to the critical. The data shows that a majority of these systems are actually stable at this point in time. Now, something to be added, stable is just that there's no exchange of objects. An unstable system means there is a higher chance of exchange occurring, so it's not considered stable. But a stable system actually has no chance of this exchange happening based on what we know at the moment. Now, 13 out of 14 of these systems, which we don't have all the correct variables at the moment, so that's why there's only 14 instead of 30, are stable. So that's really awesome in the long term. The chart at the bottom shows that if the blue is less than the orange, it's stable. But we have system 11, which is HD 188753, is not stable. And looking at the masses, it is very understandable why, as well as the fact that it's really a closed system. So on the understanding that 13 out of 14 systems are stable, according to Hill, knowing the connection between stellar masses and the semi-major axes is key in understanding if a system is stable in the long term. In the future, there are more values to be calculated, and once the catalog has been completely compiled and everything has been referenced and checked, the goal is to take the same equation and include the planet to determine if the planetary system is stable, an example of which is shown below in Figure 3, which is actually how most orbits are, looking at how they are set up. Then, when the planetary system is determined to be stable, the habitable zone equation will then be used to determine if the planet is residing in the habitable zone of the stellar component or its host star. I wish to thank Dr. Muslak and Dr. Kuntz, as well as the UTA Physics Theory group, for helping me with working through my issues, as well as Mary Alice for being there for me. I would also like to send thanks to Dr. Billy Quarles at Georgia Tech for helping me with the Python code that I ended up using. This research is prepared to be published and is expected to be published in the coming months. Thank you for your time.